Welcome to Process Control in Practice. My name is Margaret Bauer. Here we discuss some of the basics of process control and automation. If you want to know more, check out the book with the same title by Tore Hägglund. In this video, we have a look at the algorithm that is used most widely in the process industry, the PI controller. We'll see that the PI controller improves on a purely proportional controller and does in fact not have any structural shortcomings. In process control, we most often want to keep a physical variable y at a reference value r, and we do this by comparing it to the current measurement y, then using the error e to make a decision on what the input to our process should be. The P controller computes the control signal U proportionally to the error. U equals to K times E plus U0. When we look at the time trends of R and Y, we can see that P control has one fundamental shortcoming. Y will never reach the desired set point R. This is called the offset. The reason for the offset is that the control error will only be zero if the control action U is equal to U0. This means that we need to adjust or reset the bias automatically. This is exactly what is done with integral control, and the reason why integral action is also often called reset control. In short, we replace the term U0 with the integral of the control error. U is equal to K times E plus Ki times the integral from 0 to t of E of tau d tau. Here, tau is the integral variable over time as we integrate from 0 to t. We'll come back to that later. We can divide u into the proportional part up and the integral part ui. We can see that the PI controller has the ability to eliminate the remaining controller error by considering the following. Assume that we control a process with a PI controller and that we have a persistent control error or offset after all the transients have died out. That is, Y never reaches R. If the control error is constant, then the proportional part of the PI controller will be a constant with value Ke. However, the integral part will continue to increase or decrease, depending on whether the control error is positive or negative. The only way to achieve a constant controller output is when the controller error is E equals to 0. We can apply the PI controller to the temperature control in a distillation column, where we want to maintain the temperature at the bottom of the column by heating the recycle stream and manipulate the flow through a heat exchanger. Let's look at the time trend of the temperature Y and the valve position U. When we start up the process at time t equals to 0, the temperature must increase from ambient temperature of, say, 20 degrees Celsius to our desired temperature, say 83 degrees Celsius. We achieve the temperature increase by opening the steam valve. The time trend of UP will act in the same way. At the beginning, the P controller will apply a large signal to the valve because the error is large. But see what happens as we get closer to the steady state. The P controller stops acting altogether. Now the I part, UI, won't do anything at the beginning, but will increase as the error persists. In fact, it will get larger until we reach steady state. At this point, the I part is effectively the adjusted U0 from the P controller. It will remain that way until all eternity. Well, not really until eternity, just until we change the set point again or until a disturbance hits us. We can see why it is important to integrate from 0 to t. This means we integrate from the time we switch the controller on until now. So if we run a continuous operation, it means that we integrate from 6 months ago until now. Of course, if the controller works well, the control error is very small for most of the time, and the controller output doesn't change very much. We like to say that while the P part looks at the present, the I part considers the past. The integral action is slow because not only do we have to wait until a control error E occurs, but we must wait for it to be present for a long period of time. The I part is therefore often called slow mode. The PI controller overcomes the problem of the P controller and does not have any shortcomings in principle. Let's revisit the parameter Ki, with which we say how much integral action we would like to have. We usually don't see this parameter in the distributed control system, DCS for short, or in the programmable logic controller, PLC for short. But instead, we see an integral time Ti. This is because the parameters of the controller are defined in the equation U equals to K times E plus 1 divided by Ti times the integral. This means that Ki is equal to K divided by Ti. We can interpret the meaning of Ti by picturing the controller as a block with input E. We would like to know how U reacts to a sudden change in E. We draw this sudden change over time as a step with height delta E. As a result, the proportional part of the controller output will jump by K times delta E. The integral part will increase with the slope K over Ti. This means that after time Ti, U has grown to double the initial jump, 2K times delta E. If the process is fast, we want this doubling to be done quickly, while a slow process requires the controller output to change more slowly. In other words, the integral time should be chosen proportionally to the dead time or time constant of the process. The integral time has the dimension time, and the unit is usually seconds or minutes. However, there are controllers and systems that instead use the unit RPS, which stands for repeats per second, or RPM, which stands for repeats per minute. What this means is how many times the increase caused by the P controller is repeated each second and minute, respectively, by the PI controller. For example, if a controller has an integral time of 15 seconds, its unit can be specified as Ti is equal to 15 seconds or is equal to 15 divided by 60 minutes, which is a quarter of a minute. That means 1 over Ti is equal to 4 RPM, so it's repeated 4 times per minute. This means that after 1 minute, the integral action will have increased the control action 4 times. To sum up, the PI controller overcomes the problem of the offset of the P controller by automatically adjusting the bias U0. It does so by considering the past. PI control is also called reset or slow control. The PI controller does not have any theoretical structural disadvantages. It's not all rosy though. There are some implementation problems we must deal with later. For example, we need to implement the integral part recursively, or otherwise we have to remember the error from 6 months ago when we switched the controller on. Another problem arises from the limitations of the actuator, and that problem we call integral wind-up. But we can deal with these issues, and then the PI controller is your go-to controller in the process industry. Thanks for watching, and see you again soon.